Thank you again for the introduction. I'm pleased to be sharing with you today some of our research on leveraging MR-guided focused ultrasound to potentiate immunotherapy for glioblastoma. At this point, there have been several lovely introductions to GB, but I'll just reiterate that, of course, it's the most common and aggressive malignant brain tumor in adults. Despite the current standard of care, it remains nearly intractable due to its highly diffuse and invasive nature within the brain. And of course, patients face a dismal prognosis, despite a lot of different therapies, which tend to be limited by sort of two local regional barriers that we tend to think about. And Dr. Carpentier mentioned earlier that there's sort of a gradient associated with the integrity of these barriers in the presence of GB. The first is the blood tumor barrier, which is a heterogeneously leaky microvasculature that creates high interstitial fluid pressures within the region of the brain tumor and is typically characterized by the presence of the enhanced permeation and retention effect. The BBB, or blood-brain barrier, is largely absent of the EPR effect and consists of highly intact tight junctions lining endothelial cells, as well as associated restrictions on convective and diffusive transport. Moreover, the BBB can also protect the infiltrating margins of the brain tumor. So with this in mind, we know that focused ultrasound can induce blood-brain barrier disruption and increase delivery to the brain. However, there are several hypothesized intersections that we'd like to begin unpacking between FUS and the cancer immunity cycle. So first, I'll run through the cycle just by saying that, typically we're presented with a tumor that has cells that can release antigen, which are molecules that can be recognized by the immune system. These antigens can be captured by antigen-presenting cells like dendritic cells and M1 macrophages, either by way of free drainage of antigen or uptake by these APCs. The antigen can then be presented to T cells that can be primed and activated, hopefully against the tumor, and then traffic back to the tumor wherein they can infiltrate, proliferate, and hopefully exert their cytotoxic effects. There are several places where we believe that intervention with focused ultrasound could potentially synergize with this cycle. First is that with the various perturbations to the tissue that we can induce using FUS, we can increase cell membrane disruption and hopefully alter the profile and amount of antigen that is available for recognition. Moreover, antigen alone is not enough. APCs need context, and so increasing damage-associated molecular patterns, or alarmins, is another hypothesized intersection. Almost finally, there can be increases in cytokine expression. Some groups have demonstrated this in other tumor models, as well as decreases in immunosuppressive cytokines in the circulation, increases on adhesion molecules on the endothelial cell surface, and then finally, by increasing permeability, we can hopefully increase infiltration and proliferation of T cells. So with this in mind, we've designed a set of experiments that are essentially aimed at assessing the impact of peak negative pressure associated with focused ultrasound BBB and BTB disruption on anti-glioma immunity. So what we're looking at here is just a schematic of our MR-guided focused ultrasound setup. And we have an experimental timeline wherein we implant the GL261 Luke2 cells in the brain and 2 weeks later intervene with focused ultrasound BBB and BTB disruption. Subsequently, a week later, we assess the immune sequelae by flow cytometry. And we have two panels, T cells, for various T cell markers as well as myeloid markers, but I'll only be delving into a few of those today for the sake of time. So the contrast-enhanced T1 weighted MRI images that are presented here just kind of demonstrate the effect of BBB opening at two different peak negative pressures, 0.4 and 0.6 megapascals, on the tumor. So we identify it by contrast enhancement, overlay a 4-spot grid of sonications that overlaps a bit with the margins of the tumor, and then open the BBB as demonstrated, where the yellow arrows point. So first, delving into the innate compartment, one of our observations has been that we're actually increasing dendritic cell maturity, not only in the tumor, but also in tumor-draining cervical lymph nodes, as well as meninges. So the figures here show, on the top row, percentage of CD86 dendritic cells out of the total CD11C population. CD86 is one of many markers of DC maturity, but here we see that in the 0.6 megapascal exposed group, there's a significant increase in CD86 expressing percentage of DCs in the meninges. By way of mean fluorescence intensity, which really gives you a sense of expression of these markers on a per cell basis, there's a significant increase in CD86 expression conferred by the 0.6 megapascal treated group in both the DCLN and tumor. Moving into the adaptive compartment, we're seeing that there are some increases in CD8, or some fluctuations in CD8 positive T cells. First, I'll point your attention to the fact that when we look at CD44 positive subsets, in terms of a percentage of the CD8 positive compartment, we actually don't see that there's a significant modulation of CD44, which is a marker of antigen experience. That said, there does seem to be a pretty high percentage in general of CD44 positive cells. Moreover, when we delve into the PD-1 expression within this particular compartment, we see that out of the CD44 positive CD8 T cells, there is a significant increase in PD-1 positive subsets within that, again conferred by 0.6 megapascal FUS exposure. Moreover, this reflects in the MFI as well as absolute frequency. So finally, we're not just interested in PD-1. We've been looking at a host of other checkpoint molecules, again with an eye towards checkpoint blockade. So we aren't seeing that other molecules like TIGIT or TIM3 are modulated as a function of focused ultrasound, but the significant increase in PD-1 expression does sort of lend rationale for us pursuing anti-PD-1 therapy or checkpoint blockade in the very near future. So with that being said, I'll just conclude to say that we've demonstrated here that BBB and BTB disruption with focused ultrasound and microbubbles can elicit mechanisms of immunity in a glioma model independent of drug delivery for the time being. And so our ongoing studies, first and foremost, aim to functionally characterize the immune cells that I've talked about a bit today, but also in the future couple this approach with checkpoint inhibitors. And so with that, I'd again like to thank my advisor, Richard Price, our wonderful collaborators in immunology and radiology who have enabled this to happen. A very special shout out to a postdoc I work with, Dr. Ali Witter, who has enabled a lot on the immunology side, and of course, all of our funding sources and the Focused Ultrasound Foundation. Thank you.
Very nice, very nice. Do anybody has a question? Yeah. I see that Natasha has the award also, the Young Investigator Award. Congratulations.
Usually when you look at histology and you try to find how much TTLs are in the tumor, you see that there is enough in glioblastoma. It's not that we don't have immune system. It's the immune system understand that this is a self and don't recognize. This means that to recruit without any other ways to recruit the self immune system to the tumor does not help in therapy of glioblastoma and immune therapy. You need to build a molecule that you can introduce that will do an immune storm which don't recognize the cell as self. And that's the important thing. Because there is enough of TTLs in the tumor.
Right, so there is an identified neoantigen for GL261 in the literature, so something we're working on is building a dextramer to actually be able to parse out the question of, you know, these general host cells versus those that truly recognize the tumor, if that sort of begins to address the comment.
So on histology, when you look at the meninges,
Yes.
You see mature dendritic cells. Do you now start seeing an inflammatory response in the meninges in response to the PFUS? Or is this in response to basically the implantation of the tumor and then?
So we've done sham controls and don't necessarily see the same response. We do see somewhat of a B cell response, but we haven't really parsed out that question yet. So to speak to the difference from implantation to FUS exposure, we're kind of more confident that this is truly conferred by FUS. That said, I should clarify that all of this data was flow cytometry based, so I'm working on building out the histology for meninges and brain right now.
Thank you very much.
Thank you.
Yes, go ahead, sure.
I think there's one more question.
For Natasha, yeah.
One more comment. A great deal of this notion of taking a relatively non-immunogenic tumor and rendering it immunogenic can be elucidated by comparing what radiation does to all of the processes you pointed out. But one process is especially interesting to me in your studies, and that is, are the antigens altered? Because if the focused ultrasound alters the antigens enough to stimulate a different either type of response or, more importantly, magnitude of the response. So I'd be interested in your comments about that and any comparisons you have to using ionizing radiation as a comparison.
So unfortunately, we have not done the direct studies ourselves. There are some studies out there that have done stereotactic radiation in this model, but unfortunately, there's a challenge in being able to do the one-to-one comparison between our results and theirs. So while we haven't done radiation, I think that's a very interesting comment and suggestion for us to maybe do ourselves. To speak to your point about antigen, we're actually trying to build out, again, these things are in the works, but we're trying to build out another iteration, an engineered version of this model that would enable us to actually track antigen, flow and drainage out of the tumor, and uptake by antigen-presenting cells, so that we can really understand mechanistically whether that hypothesis is demonstrated. So, thank you.
Thank you.